as mentioned, Gregory Cohen is the associate professor and from the Neuromorphic Systems and deputy director of the International Centre of Neuromorphic Systems at Western Sydney University. He leads neuromorphic algorithms and space applications for ICNS. Prior to returning to research from industry, he worked in several startups and establishing engineering and consulting firms, including working a consulting engineer in the field large-scale HVAC forum from 2007 to 2009. As an electronic design engineer in 2009 to 2011, as an expert consultant for Kaiser Economic Development Practice in 2012. He's a pioneer of event-based and neuromorphic sensing for space imaging applications, unsupervised feature extraction, bio-inspired machine learning, and neuromorphic computation systems. So it's my great honor to introduce Greg. And Greg, over to you.
Well, hello, everyone. Thank you so much for that. And in fact, I'm actually going to talk about quite a bunch of the things you mentioned in my introduction there as well. So my talk today is about biologically inspired space imaging with neuromorphic sensors. And there's a bit to unpack there. But really, what I'm going to be talking about is using neuromorphic sensors, specifically vision sensors, and how you can apply them to really interesting use cases in places where you really need to care about power consumption, about reliability and robustness. So really about the edgiest of edge applications you can get for these sort of sensors. And I'm going to show you how, by changing the sensor and the data you get out of those sensors, you can really simplify the processing and how you deal with that information. And by changing the sensing, you can actually change the entire way you approach the problems that I'm going to talk about today. And if you can sense in a better way, you can process more efficiently, and you can start getting towards sensors that solve real world problems at power levels that just aren't possible the way we do it currently. So maybe I should have started by giving you my quick summary of neuromorphic engineering. And perhaps the way I like to do this is say, this is really my take on neuromorphic engineering, because it is quite a broad topic. And I think everyone sort of has their own way of defining it. But I look at neuromorphic engineering as essentially the opposite of biomedical engineering. In biomedical engineering, we take technology, we put in biology to solve problems. But in neuromorphic engineering, we kind of go the other way. We look at how biology solves problems, and we take those ideas to build real world systems right down to the silicon level, like silicon cameras that I'm going to talk about today. And we do that to try to get towards the sort of robustness, the reliability, and specifically the power efficiency of biological systems. And I mean, a great example is this dragonfly over here, because what's interesting about dragonflies is when they're hunting mosquitoes, they don't move to where the mosquito is. They actually move to intercept the mosquito. So they're predicting where the mosquito is going to be, and they intercept it in midair. That's a really challenging visual task to do. And what's amazing is that they don't have the greatest visual system. They certainly don't have a big brain, and they do this on a fraction of the energy that it takes us to do with far more computing hardware. So the upshot is really the dragonfly is doing it the easy way, and we're doing it the hard way. So neuromorphic engineering, we're saying, how does the dragonfly sense the world around them? How does it process that information? How does it make rapid decisions to solve tasks at that sort of power level? And what we're saying here is that we're not going to try to build a dragonfly. We're going to say, let's try and figure out how it does that and build systems that aren't biologically possible. So we're not saying this is how biology works at all. But we're saying let's take those ideas and really approach the problem of sensing and computation in a completely different way. And the trick is that we really want to start as close to the sensor as possible, because if you sense the world in a different way, you get different data out. Even if you have really interesting processing, if you have to sense the world in a conventional way, you do have to do quite a bit of work to get it into another format. So why not sense the data in the format you want to process it in? In this case, neuromorphic engineering for the processing, neuromorphic computing, and for the sensing is in neuromorphic sensing. So I'm going to talk a little bit about sensing in the visual world, and specifically how it relates to neuromorphic sensing. So I like this little slide, which shows you two modalities, audio and visual. And it's going to really show you why the visual world is so much more challenging to process than the auditory world. And the reason really is that if you look at sound, let's just take capturing sound. Well, you have two ears, so you have two channels. And if you start looking at how much data we have to deal with, we have two channels, right? You'll hear people say that humans can listen to about 20 kilohertz of frequency. So, if we use the Nyquist theory, we double it and say we want to capture these 40 kilohertz, but let's go completely wild and blow it up to sampling at a megahertz, which is well beyond anything we need, but it sort of illustrates the point. And let's use quite a lot of bit resolution per channel. That comes to about 6 megabytes of data per second, or 21 or so gigabytes per hour, which is a lot of data, but it's not infeasible to process that in real time even. But that's really the extent of it. That's everything we could ever care about in the auditory domain. And, that's before we even start compressing the data and working within efficient ways. That's why audio is, I wouldn't say it's a solved problem, but it's a problem we have really good techniques with conventional systems that get us pretty much to where we need to be at the moment. When you start looking at vision, if you want to capture the raw data behind the visual world, that's a different task entirely. You've got 3 different colors, red, blue, and green for the cones in your eye. You've got 2 eyes as well, so that's already quite a bit. And the fact is, we like 4K and HD screens, so we can see at least 192 by 180 pixels per eye. Now, you might hear people say, we start fusing images into videos at around 30 hertz. That's true, but we can absolutely detect higher frequency effects, which is why people like 120 hertz monitors, for example. So, it turns out 500 hertz flickering images we can see. So, using Nyquist again, that's a kilohertz of sampling. And when you do the math there, we're looking at about 12 gigabytes of data per second to capture everything in the visual world. And that's a lot to process. So with neuromorphic engineering, the way we're going to approach it today is to say, if we can pick the problem we want to do, we don't need to capture all of that. If we can figure out what the task is, we can build a really optimized system that just grabs only the information we need to do that task. And the closer we can do that to the sensor, the more power efficient we can be. And neuromorphic cameras or silicon retinas, which we're going to talk about in a second, are one way to do that, to capture only what we care about, or more of what we care about and less of what we don't care about in the visual world. And this is just a little graph to show you how neuromorphic sampling differs from conventional sampling. So what you see on the left is uniform sampling, which is kind of how we're used to dealing with signal processing. You divide time up into chunks and you read the values of an analog signal or whatever signal you want to measure at discrete time intervals, fixed discrete time intervals. So that's your frame rate for a camera. That's your sample time for audio. That's great. It works really well. And the great thing about it is that you get a sample at a regular interval. It's easy to predict. It's easy to process. Right? There are some problems with it, though. That comes to the fact that if you set your bin size too wide, you can miss changes like you see in that middle of the graph there. There's a complex change in the pattern that we just miss by only sampling on each side of it. That's quantization error. But also, there's no change in data depending on what happens. If nothing is happening, we still get all that data out. I call that vertical sampling. That's what we're used to. Neuromorphic technology tends to use what I'd call horizontal sampling or threshold sampling. Now, instead of dividing time into nice, neat bins, we divide the magnitude of a signal. That has some interesting properties in that we only want to see when the magnitude of the signal crosses those boundaries, and we emit those here as events to say, oh, we crossed this threshold or we crossed this threshold. That has some really interesting properties in that time is now fluid. The events occur when they occur, and our time resolution is just how fast we can mark those events as they cross the lines. Just as we can change the frame rate by moving the vertical bars on the uniform sampling, we can actually change the sensitivity by increasing or decreasing the way we divide up the magnitude. And that way of sensing has some really interesting ideas, because if nothing is happening, the signal doesn't change and you get no data out. When things do change, you only get those changes. And that's essentially what we're doing in the pixels of the neuromorphic cameras I'll talk about in a second. But it's just a whole different way of sampling, and you can start to see why the data that comes out of these, it's fundamentally different to this nice uniform data we're used to. But if you work with it in the format it comes out, you can build really efficient systems. I'm just going to quickly show you this slide. This is actually something you might have seen. It's one of those mice where you move the ball with your thumb rather than the mouse around. This was actually built by the director of ICNS, the research lab I work in, Professor Andrei Fernscheik, who built this in 1994. And I really like this as an example because often you find neuromorphic engineering is kind of put in the same bucket as quantum computing, which is, an exciting new technology. But whereas quantum has been 10 years away for the last 40 years, neuromorphic has the opposite problem. We've actually been around. This is a neuromorphic application that's been around since 1994, but we just didn't do a great job telling people. The difference between us and quantum is we don't have a great marketing department. Well, we do have technology right now that does this. So just to give you a sense of, interestingly enough, by the way, this chip is based on how Dragonfly Vision works. So there's some nice parallels there as well. So let's talk about the cameras themselves. So these are neuromorphic sensors. We're actually building one here at Western Sydney as well. But essentially, they differ from a conventional camera in a few ways. They have this idea of that threshold sampling. So each pixel on these cameras are independent and asynchronous, and they only detect changes in contrast, and only when they happen. So if you point one of these cameras at a static scene, you get no data out. If something moves from the scene, only those affected pixels send you that information, and they get those events, those change events, as fast as they happen. With the cameras we have now, they're about microsecond resolution. So you don't have frames, you don't have exposure times, you don't get saturation effects in the same way, and you don't get motion blur. And this is great because it lets us do some really interesting things. But the problem is conventional techniques for computer vision, for machine learning, they don't work as easily. They don't directly apply because we don't have frames. We don't have nice fixed bins of time. And the moment you start binning this event into frames or buckets or whatever you want to call them, you start losing some of the benefit. You still get some of the benefit of these sensors, but you have to be careful to try to stay working with them in the stream of events, this activity-driven mindset. So instead of pulling frames out the camera and searching through them, The camera's going to push you information only when something's relevant. So I'm going to show you some demonstrations of what this data actually looks like. This is a recording from one of our buildings at Western Sydney University, looking down on a construction site. On the left, you can see a conventional camera. On the right, you can see one of these neuromorphic cameras. A yellow pixel on the right-hand side means that the light intensity, the contrast of that pixel went up. A blue pixel means it went down. And what you can see is the event-based camera automatically just captures all the things that you care about, all the things that are moving and changing. It removes all that redundant information. You can see the people walking around, you can see the cars driving, you can even see the rain coming down. The difference is the frame-based camera produces a frame at a constant frame rate, so you get 83 megabytes a second. The event-based data, on average, is about 60 megabytes of data per second. But the trick is we're getting that with a really high time resolution. So I'm making frames from that data, which is exactly what I told you not to do. But for visualizing, it's easy. But I can make those frames at whatever frame rate I want. So I can play the same video back. I can render those frames from the event-based data 10 times slower. And you can see on the right-hand side, we get this nice smooth motion from the event-based camera. But now we have 3 frames a second from the conventional camera. We start running out of frames. And you can start seeing why, if you work with the data and the way it comes out, you don't have to worry about not having enough frames. That data has microsecond resolution on those changes. But perhaps the most important thing about this data is that the data on the right is not a video. It's rendered from this event-based stream into a video. But what it really is something completely different. This is a great demonstration. When you take a video, you essentially stack image frames on top of each other, right, to make a sort of volume with time on the vertical axis. The event-based cameras, by contrast, only capture those changes. You get this continuous stream of events from the objects in the scene. And if you look at the right-hand side, you've got time on the vertical axis, and you can see how those cars, those people, are really easy to track through time as they move. Far easier to find them in the scene. You don't have to search this big volume of data to find what you care about. The objects that are changing are the ones that send you the information straight away. This is why we can track things more easily, but we can also get velocity and acceleration of those objects too. You can see the space we're looking through is actually far sparser than the one with the static frames stacked on top of each other. And when we work with that data in the frame, in the sort of format that it comes in, we can unlock some really, really interesting ways to process it at far lower levels and with far less data, because less data is less data to process, less data to transmit, and less data to store. And all of those consume power. So I'm going to show you one other interesting thing about these cameras. I said each pixel is independent and asynchronous. And what I mean by that is that they all look for these contrast changes around whatever set point they just saw. So you can have some looking really bright parts of the scene and some very dark parts of the scene. And that gives you this really wide dynamic range. And the really good way to illustrate this is by looking at the lunar eclipse from last year. So what you're looking at here is the moon. And what you're seeing here is the actual lunar eclipse with the line that you see in the middle of the moon there being the line of the eclipse. So everything above that line is fully illuminated by the Earth, and by the sun, and everything below that line is eclipsed. So you can see in that conventional image the difference between the two sides. But what's interesting to note is that we can see features on both sides of the moon at the same time. We don't have to pick which one we want to have saturate and which one you have to see different, like you would with a conventional camera. So this is just an example of how, just by using the cameras and the way they are, we can already unlock some interesting applications. So this dynamic range is really interesting and has some really interesting applications for space imaging. And that's what I'm going to talk about right now. I've got 2 really interesting ones. The first one is the astrosight. And the astrosight is the technology we've built around these neuromorphic sensors for looking up from the ground, from telescopes on the ground, for a really interesting problem called space situational awareness. And it's a term that I think is probably becoming more and more widely known. But essentially, we've been launching things into space since about the 60s. And it turns out we've done a terrible job cleaning up after ourselves. So there's a lot of space junk up there. There's a lot of satellites up there. There's a lot of defunct satellites in these orbits where they'll take years before they decay. And with everything we launch up there, the risk of collision between these objects goes up. And with crewed spacecraft, for example, that's a significant problem. And we really rely on space infrastructure for almost everything we do in this world. Everything from, GPS to credit cards to communication systems. That's all our critical infrastructure. And the truth is we don't know where half the stuff is. So the ability to be able to find and track and detect and monitor the volume around Earth in terms of the objects in there is a really critical, important one. And neuromorphic technology, when you put it on a telescope, has some really interesting advantages for doing that. You get to leverage that high dynamic range that I showed you. And that lets us see in conditions where you might not normally see and have really bright and really dark parts of the scene at the same time. But it also lets us leverage the fact that in space, everything is moving. So we can actually do things like image whilst the telescope's in motion. And that can change the whole way you approach this task. Normally, you do space situational awareness with expensive radars, hundreds of millions of dollars to build, tens of millions to operate. They're big, they're noisy, they emit radio signals. They're not great. The other way to do it is with optical telescopes. And that's great, but you run into these problems where you're limited by weather, you're limited by cost, you're limited by the fact these are moving parts that can look at one satellite at a time and follow them. So we started doing this work in about 2016. And this is actually a nice little example. On the left is the recording from the first ATIS camera I used in 2016. And that streak you saw through there, that's a satellite moving through the field of view. To be honest, we had no idea what this would look like when we put this on a telescope. We just thought that'd be really interesting to see what happens. And that was kind of the aha moment when suddenly we're just sort of, taking a break, looking at the data from the camera, the telescope wasn't moving, and this thing just struck right through the field of view like that. And so after trying to figure out what it was, we realized, oh, it's a satellite. And from that, everything sort of just developed from there. What you're looking at the right-hand side is where we are currently now with our AstroSight system. We're using a far more modern camera, the Prophecy Gen 4 event-based sensor that you can buy from Prophecy at the moment. And with a bunch of really interesting processing steps, what you can see here is that we're actually looking at the stars moving through the field of view as we're following a satellite. So we're moving the telescope to keep that satellite in the yellow circle in the field of view. And as we're doing that, we find the stars around it, and we actually figure out where in the sky we're looking based on the stars, and we can give that position of that satellite continuously in what they call sky coordinates. So we're saying where exactly that satellite is, and that's what you need for the space situational task, is to be able to point to the satellite and say, okay, I can tell you where that is accurately, and you can update your model where you think it is in orbit. And the fact is we can do this in a completely different way by being able to move the telescope and see everything, because normally if you want to follow the stars, the object you're looking at will be a streak, because you have to integrate. If you want to look at the object, the stars will be streaks, because you have to decide which one is going to move and which one's going to be stationed with a conventional camera. But with these cameras, everything can be moving all the time, and you're leveraging that temporal resolution to do that. So what do we do with these things? Well, so once we discovered we could put them on telescopes, that really changed the whole way in which we approach the problem. So instead of building conventional telescope observatories, which are essentially large buildings with a concrete pad on the ground and a big building built to get rid of every bit of vibration, every bit of motion, we realized, well, actually, we don't need to do that. To be honest, when I started out, I used to tap the telescope with my fingers to help me see things, because I would shake everything, and I'd actually see the stars better. If you do that in an astronomy observatory, they will kick you out, and they'll pretty much ban you forever, because they want to get rid of every bit of vibration. But it turns out, if you are not integrating, you're far more capable of actually using the motion to help you. So we just embrace motion. And that's one of the reasons why we can now move the telescope, but also makes us less sensitive to these motions and these vibrations. So whilst everyone else is trying to stabilize the telescopes by building buildings, we build them into shipping containers. So you have the shipping container, you put it down, the roof slides off, the telescope comes up, it does its observations, packs itself away, and then you can put it on a truck, a boat, a ship. There's a whole industry around moving these things around, and then redeploy it somewhere else. If there's bad bushfires in Sydney, move them somewhere else. There's higher than average rainfall expected, move these things within 24 hours. And this is a whole idea that no one else has really been able to do, because you can't do these as easily with conventional sensors. We can also have two looking at the same object and do ranging, for example. But essentially, this whole technology comes from the fact we changed the sensor at the back of the telescope. So a tiny bit of silicon that does the sensing enables us to do this whole different technique. And this is, of course, where you really want to use neuromorphic processing, because these things are going to be put in the middle of the desert where there is perhaps power, because you can use that from solar panels, but you still want to get this data back to a central point to look at it. And if you're in the middle of nowhere, you don't necessarily have the infrastructure to have high bandwidth connections. So you really want to do the processing as close to the sensor as possible. So all you saw there with the AstroSight when we do the stars, that's all done locally using essentially embedded machine learning techniques to do that. And that's kind of an interesting thing in itself, because we had to develop all these techniques from scratch. When we started, we would just sit in the AstroSight, and this is actually what the inside of that one of those AstroSights looks like, doing everything by hand. And after trying to figure out what we actually had to do, what the tasks we were trying to do looked like, we automated it. In fact, COVID really helped here, because we weren't allowed to go into these for about a year. So we built entirely remote and then entirely autonomous systems to do that. So this is what it looks like now when it's running. You see the telescope goes up, it does its observations. You can see how it's moving from satellite to satellite. And on the top right, you can actually see the real data from the satellite as it moves around and takes images and recordings. And this is all done in real time with the data streaming back to us, so that we can actually tell people where the satellites are, which I think is kind of an interesting application for this technology. So the AstroSight really uses this from a terrestrial point of view. And so it's probably our most exciting demonstration of how using neuromorphic technologies can really let you approach a problem in a whole different way. Now, the next thing I'm going to talk about is the other side of the problem. So we reverse the situation. It's a project we did with the US Air Force Academy called Falcon Neuro. Here we have the cameras on the International Space Station looking down at Earth. So these are two neuromorphic event-based cameras. These are the Davis sensors, the Davis 240C from Innovation. And we heavily modified them into a payload package, and we put them together with some processing in a payload that was launched at the International Space Station at the end of last year. They were attached at the beginning of this year, and they've actually been operational since. And that's a really interesting project. And you can see why space is actually a perfect application for both neuromorphic systems and essentially tiny machine learning systems, because space, you are limited by power, you're limited by space, and you're limited by bandwidth. So you need to be efficient in every way you can. Neuromorphic cameras, which are fast, so high speed, low power, and low bandwidth sensors, are perfect for generating the data. But even then, you want to try to do as much processing as you can, as close to the sensor as you can, in order to survive in these sort of extreme environments. And in fact, the closer you can move your algorithm into the sensor surface itself, the more efficient you can be as a problem overall. So why are we putting these up in space? Well, there's a few reasons. The first one is the science goal for this project, the fundamental research we're looking at, which is called transient luminous events. So these are essentially upside down lightning. So if you have a storm with clouds, usually you see lightning that strikes from the clouds to the ground. Sprites go the other way around. You essentially think of them as electrical discharges from the clouds up into the upper atmosphere. And they're kind of interesting. They're really hard to study because they're extremely bright and they're extremely fast, which makes a sensor that is non-integrating and very good at catching high-speed phenomena perfect for this sort of application. And we don't really know how often these occur, what they do when they occur. They certainly ionize parts of the atmosphere, but maybe they pose a threat to high-altitude aircraft. Maybe they pose a threat to satellites. They're really hard to study. They're actually usually captured purely by accident rather than on purpose. And the idea of launching 2 neuromorphic cameras into space was to say, can we observe these phenomena? And with the cameras we launched up, we don't have great resolution, but we want to see if we could figure out the frequency and the distribution of these events around the Earth. So we had 2 cameras installed, one looking straight down, the nadir camera, and one looking at the horizon in the direction of motion of the ISS. So for lack of a better way of saying it, if you're looking through the front windshield of the ISS as it goes, not that it has one, but that would be the RAM view we're seeing now. And we look for lightning in both of those. And this, what you're looking at here, is actually the first neuromorphic data from space. So this was acquired on the 10th of January this year as we passed over Honduras. On the right-hand side there, you can actually see the Falcon Neuro instrument attached to the Columbus module of the International Space Station. And that was 2 neuromorphic cameras built by us in Western Sydney, integrated into a payload with the United States Air Force Academy, and successfully launched. And we did this amazingly during COVID, where we had to build it in 2 halves because we couldn't travel to the US and they couldn't travel here to integrate the 2 halves of our payload. So it's a huge technical achievement for the technical team here at Western Sydney University who managed to build this and get it to work and remotely debug it, across continents and time zones. So what you're looking at here on the left-hand side is the first data. Now, we've overlaid this on a map of the Earth from Apple Maps. And that insert on the left, that HDEV camera, that's a conventional high-definition camera on the International Space Station that streams live data back to Earth. And that's what a conventional camera takes an image of. That sort of purple strip you see in the middle there, that's the data from the neuromorphic cameras we have there and the processing we do on it to make it look like an image. Because remember, I said the data produces the stream of events. Now, to make it into something that's easier to see, we can process that to make it into a 2D image. We can essentially motion compensate it by squeezing it down. And what you're seeing here is that image overlaid on the Earth. You can see how well it matches with the coastline specifically. Now, that white box at the bottom, that is actually the resolution of the sensor. The sensor only has a 240 by 180 pixel resolution. So it's quite an old sensor by comparison. To give you a sense of what we're using now, we're using HD sensors, which are closer to the HDEV image you see there. You can imagine what that would look like if we had that imaging range. But as the Earth turns and we look down on it, we can actually use the fact that we know the rotation of the Earth, or the relative movement of the Earth from the ISS, to essentially build up this long continuous strip of data that becomes an image. And we can run that as long as we have memory. So as long as we can keep up with the computation, and as long as we can store it in memory, we can produce these really long continuous images of Earth. And what's particularly exciting about that is that we're not actually capturing an image. So if something is moving in the field of view, we'll see that as well. That actually becomes quite easy to detect because anything that's moving doesn't correlate with the motion we expect as the Earth rotates. So it's easy to pull out and say, hold on, that thing's moving independently. Now, I should say the only problem we have is that we did fly a low-resolution sensor with optics that give us about 300 meters per pixel. So it's not the world's best resolution, but we actually have a follow-on mission that will probably improve that quite dramatically. But still, given the sensor we have, the results I show you here, you'll see that there's really promising applications for these sensors in these difficult environments where you can really define the task. So I'll give you a little bit of what we call the world tour. in the ISS data. And we'll start looking at the Honduras recordings that you see here. This may not run so well over the internet, so I apologize. And, it might be worthwhile. I do have this video somewhere online if you want to watch it afterwards. But as you can see here, what we'll do is we'll fade out the transparency and see what looks like clouds are actually related to the structure of the mountains behind us. We can see far more detail than we thought when you actually delve into the data. And this is an interesting problem because sometimes by making frames, we actually lose the information that we think is there. Another interesting thing about these cameras is that they work at night as well. So normally if you take an image at night, it's really hard to see. This is probably the best night image of the ground over Bordeaux. And when we overlay our data from it, you can see we can actually see the road network leading in and out of Bordeaux. And you might see that really bright light to the left side of the city. That's actually a lighthouse on an island there. So these cameras, without any changes, by just leveraging their high dynamic range, work just as well at night as they do during the day. And those roads are smaller than the 300 meter per pixel resolution we have with the sensor. So by using the motion, we actually get sub-pixel resolution. And the last thing I'm going to show you from this video is actually the Suez Canal of all things. And that's particularly interesting because the Suez Canal has ships in it. And what we actually did was pull the shipping data for that day. And what we can see here is those are all the ships. And if you look at our data, you can see the dots, the purple dots just to the left of the ship, kind of line up where the ships went across through there. And it really goes to show that we can see these ships. And they're big, so they're about the 300 meter pixel resolution we can get. But the fact that we can see ships with these cameras is a really exciting and promising thing. What you're seeing there is the runway at Sharm el-Sheikh Airport at the bottom there. And that's actually really nice for us to figure out how to compress the data down back into an image because we want the runways to be nice and straight. So the next thing I will talk about quickly now is some processing with neuromorphic sensors. And I think it's just an interesting point to end on, which is to say, well, so I've shown you some really interesting places where you can use neuromorphic sensors. I've shown you some really interesting applications of them. And what's nice is we can really define those applications well. We can say this is what neuromorphic sensors excel at. And now I'm going to talk about, well, what do we do with this data? How do you process neuromorphic data in a way that really showcases the performance of it? And one of the things we do find is that if you start trying to compare and contrast neuromorphic solutions to conventional solutions, you run into trouble that you tend to land up having to build problems that are based around frames for conventional cameras to compare to. And that doesn't really do justice to a sensor that doesn't produce frames. Then you start having to take the data from these cameras and put them into frames. So if you want to try to assess the performance of these cameras, it becomes a bit more difficult. And the answer really comes down to we need to set benchmarking tasks. We need to find a task to measure performance on. So, things like signal to noise ratio, for example, are much harder to define with an event-based or neuromorphic camera than it is with a conventional camera. So to get around that, we need to use different processing techniques. So one of the things we did, for example, was set up a little toy problem where we drop these model planes freehand to a box. And I'll talk about that in a second. And essentially what we do there is build these event-based feature detectors where the camera pushes data to us and we start matching those to features. And then those features produce feature events. So, well, I saw this very specific shape at this very specific time. And then that essentially outputs in the same format, this event-based format where only if I saw that feature do I emit an event. And then you can essentially just build layers of those to sort of start tackling really complicated tasks. So if we look at that little plane dropping example, we use these little model planes about 10 centimeters high, dropped them freehand in front of a camera. This is about 6 or 7 years ago now. And the idea was that can you just identify which plane it is in the few seconds that it's in the field of view? And we had this really interesting biology-inspired algorithm that does this competitive learning technique where it actually starts learning the features it's seeing just as the planes fall through the field of view. And it turns out you don't even need a complicated network. You can get away almost with the linear classifier once you have really good feature detection. And you can actually build this directly into the sensor. So what happens is as it sees planes, it starts learning plane-like features. It starts using those to identify which plane it is. And what's particularly interesting is that we can often tell which plane it is just by seeing the tip of the nose cone, because it's not just what the feature looks like, it's how it moves to the field of view. And from that, we can get really, really high accuracy really, really quickly. And I think the last example I'm going to quickly talk through is just this staring example. So this is a simulated example, but it gives you a sense of how you can build these and stack these learning systems on top of each other. So here we are looking at a bunch of just a sort of view of the ocean. And what you can see is the waves moving nicely. And we can build this network that just learns the waves and says, okay, cool, these are waves. And just anything that doesn't look like a wave, pass on to the next layer. Then we get these birds flying through the field of view, as you can see over here. And they are easy to spot because they're completely different in terms of the features they generate. So essentially, we're building networks that try to explain away the data that we're getting out of these cameras, all in an event-based way. So once we've seen all the wave features, those events that are left over get put to the bird features. But if you wait for long enough, what you also notice at the top there is how much data we're reducing from. It's just orders of magnitude down. But when something completely unexpected happens, there's neither a wave nor a bird feature, like a whale spot like that, we just get that information, just that information alone. And that small amount of information to process is what you really care about. That's your signal. So by building up these layers and layers of expectation systems, right? And this is all very low power processing by comparison, because when nothing is happening, you get no data out. And only when you see something interesting do you have to fire up more and more processing. And then you can still use that to trigger more expensive processing or more expensive sensors. And I think this is really a good way to show you how you can go from neuromorphic sensors all the way through to a real world application and use that to try get towards the power efficiency, that reliability, and the robustness of biological systems. And I think that's probably a good point to end it on. Just in case anyone is interested, we do offer a Masters of Neuromorphic Engineering at Western Sydney University, which covers all these sort of topics and more. But if you have any questions, I'd be more than happy to quickly go through them now.
Great, Greg. That was amazing. That was thank you for your insights and time, and definitely neuromorphic. I guess engineering and chips for me is a very and the way you've expressed it, right? I mean, for me, I can see the whole idea of actually doing the processing on a chip and minimizing the amount of data and bandwidth and everything, which is key, especially if you're looking at space, right? We don't have that capability. So, thanks so much for your insight. Now, there is one question which we have from Arindam, and he says, fantastic talk, Greg. I'm curious about the noise filtering on the AstroSight system. Do you specifically look for streaks as a signal and do some form of matched filtering? That's from, yep.
So it's interesting because the current generation of neuromorphic sensors are actually far better in terms of the noise they produce than the older ones. So we had built all this complicated noise filtering algorithms for those sensors that don't actually apply. The current generation of sensors are commercial grade sensors, and they're fantastic for that. But on top of that, we've realized that you actually want to work with the noise rather than reject it. So you want systems where they actually process the signal and the noise together, because to be honest, in neuromorphic systems specifically, it's hard to tell what is signal, what is noise. And often you find that once you've removed what you think is signal, you go back and look at the noise, and there's actually more signal in there that you see once you've essentially explained away the events you see. So we've actually gone away from the sort of matched filters that we used to use. And then essentially now we're doing this sort of iterative expectation-based processing that I talked about at the end there.
Great. No, thanks for that. And we've actually got another one that's come in from Brett Warnicki. Any thoughts on expanding these sensors to be hyperspectral?
Oh, absolutely. To be honest, that is a really interesting application that's pretty dear to my heart, because if you start looking at infrared, for example, you only care about changes in the infrared spectrum. No one wants pretty infrared pictures. So they're just much harder to build, and there's a lot more cost involved with them, and there's just operational constraints. But absolutely, that's one of the really exciting directions for this technology going forward.
Great. Thanks again. And Brett's actually asked another one. Have you considered tracking submarines using these sensors, looking at the ocean surface?
Yeah, absolutely. It's just the ocean is much more difficult than you think. There's a lot. Everything's always moving. Everything's always wet, and salt corrodes everything in its parts. So it's a challenging application, but an interesting one to explore for sure.
Yeah. Okay. Last one, I think. What kind of processor would you need to use those sensors? Would it be better having a neuromorphic CPU? Well, I think that's I'll let you answer that. But yeah.
So absolutely. And the truth is that we actually have to timestamp the events that come out the cameras, because we don't have some sort of compatible processors that can run real time. But if we had neuromorphic hardware that ran fast enough, we wouldn't have to timestamp the events. We'd literally process them as they arrive. And that just drops the amount of data by a factor, probably in half at least. So that's the goal, and that's what we're aiming to do. And then if we can put that in the silicon next to the camera, well, that's how we get towards the sort of power efficiency I was talking about.
Fantastic. Well, thank you for your presentation. It was really insightful, and thanks for everyone for hanging around and asking the questions. Good. Once again, we want to thank our sponsors, Tiny Edge Impulse, one of the leading what's called platforms for EdgeML and using tinyML applications. Our executive sponsors, Qualcomm, who have advanced AI research to making efficient AI ubiquitous, both hardware and software. Cintiat, accelerating your edge compute. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Kilkatech, global IoT solutions. Renesas, basically big ideas for every space. The Sony Semiconductor Solutions Corporation. Gold sponsors, Analog Devices, ARM, who also have their own talks, so please feel free to sponsor them and jump onto their line as well. FotoHub, making over-the-air firmware and model updates simple and accessible. That's probably one of the key things we moving forward, so have a look at FotoHub. Microsoft for their edge capabilities and technologies, including all their, I guess, Azure services to support tinyML. NXP, together accelerating breakthroughs that advance our world, a great hardware provider. SenseML Analytics Toolkit Suite to be able to do your AutoML capabilities. STM Microelectronics to provide extensive solutions to make machine learning easy. Synaptics, engineering exceptional experiences. And then a list of silver sponsors, including AIZip, Aeon Devices, EMSA, Greenwave Technologies, Gravity Inc., IBM, Imagimob, Etermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK and Vincent. So thank you once again for attending. I hope to see you tomorrow online to listen to some of those interesting presentations. And thanks to everyone. See you soon.